Welcome everybody. This is our 8th video in question bank slash numerical series for magnetic effects of current for class 10. Till now we have made 7 videos in this series and covered around 80 questions. I think so. And hopefully you have watched them. And if you have not watched them, then you can check them out on our YouTube channel. Name of channel is Point Basics and there is a playlist named class 10 physics, and you can find all these videos there in that one single playlist. There I have covered all the physics related chapters for class 10 with theory and question bank series in detail. And if you find these videos useful, then please like these videos, share these videos with your friends, your classmates, and subscribe to our channel. And if you want to support us financially, then you can scan this QR code and support us with whichever amount you like, because uh, it helps us to purchase new books and purchase new equipment. So if you want and if you can, then do support us by scanning this QR code, and also support us by sharing and subscribing. It is a zero cost for you to support us. So do support us, do share these videos. With this, let's start our today's video, and we will be moving ahead from question number 16, and this is our third and last exercise for this chapter. So here, let's start with question number 16. So in question number 16, it is asked that define the term current rating of a electric fuse. So we have to define current rating for a fuse. So current rating for a fuse is defined as the maximum amount of current that can flow through a fuse without damaging it. For example, if a fuse has a rating of 5 ampere, then current of value to 5 ampere can flow through it without any damage, as current exceeds 5 ampere. For example, suppose 5.1 ampere, then fuse melts and breaks the electrical connection. So it does mean that rating is defined as, rating means the maximum amount of current that can flow through a fuse, and when that value of current exceeds that value of rating, then that fuse melts and connection gets broken. and so no there is no current is flowing any longer in the circuit. So this is part number 1 for question number 16. Now let us move to second part, where it is asked name the material used to make the fuse. So fuse is made of an alloy of tin and lead. Symbol for tin is Sn and lead for lead it is Pb. So we use both of these metals to make an alloy, and depending upon the rating we require, we can decide their composition, that how many percent this will be used and how many percent this will be used. That depends upon the rating of current fuse which we require. So generally we use tin and lead to make fuses. Now name two safety measures commonly used in electric circuit and appliances. So what are the two safety measures we use? First safety measure is fuse, and second safety measure is earth wire or ground wire. These are the two safety measures which we use in electrical appliances in our home. Now moving to question number 70. In question number 17, we have to compare pattern of magnetic field around solenoid with the magnetic field around a bar magnet. This type of question we have already covered, and let me show you. Suppose we have a bar magnet. So suppose this is a bar magnet and this is north pole and it is its south pole. Then there will be magnetic field lines. We'll be using only two magnetic field lines so that we can represent neatly and cleanly. So first this is magnetic field line, and second this is magnetic field line. And direction of these magnetic field line outside is north to south. So this is north pole, this is south pole, and inside it is south to north. So this is the case for our pole magnet, and if we decide to take it for solenoid, then this is the solenoid we have. Now we have to connect it to electricity. So we have connected it to a battery with some resistance R. Why we use resistance? Because we want to control the current. If you connect it directly through without any resistance to battery, then there might be large amount of current flowing in this wire, which may lead to damage of the circuit or burning of the circuit. That's why you normally use resistance. This resistance controls the current flowing in the circuit, thus limiting any heat effect or any damages. So with this, when this type of current flows, so here directional current will be like this, from positive to negative. And when we draw magnetic field lines here, we get similar magnetic field lines. Exactly similar magnetic field lines, and that north and south pole we can decide depending on the direction of current we are flowing. If we are getting south pole here, then we can reverse the direction of magnetic battery, then we get north pole here. So magnetic field lines are exactly same, and both solenoid, if we have a long solenoid, then it just act as a bar magnet. In solenoid we have some advantage. The advantages are that using battery and resistance, we can control the amount of current flowing through the solenoid, and magnetic field produced by solenoid depends on its current. So essentially, we can control the how magnetic that solenoid can act or how much bigger magnet a solenoid can make. So we can control in this case of solenoid, but in case of magnet, its magnetic field is fixed. We cannot control it. For solenoid, we can control it, and for solenoid, we can also go inside the solenoid and where magnetic field is maximum. For magnet, magnetic field is maximum inside the magnet, but we cannot go inside the magnet. So these are the advantages and similarities for a solenoid and a normal magnet. Moving to question number 18. A compass needle is placed near a current carrying wire. State your observation following the cases two reasons. Magnitude of electric current in wire increase, the compass needle is displaced away from the wire. So we have already discussed questions like this. Now we are going to detail in brief. So suppose we have a current carrying conductor and it has some current. We are not showing here battery. So this is current carrying conductor. It is carrying current in upward direction. So if you are using a right hand thumb rule to find out the direction of magnetic field, you will find that when you view from the top, then the direction of magnetic field lines will be like this. They will be moving anti-clockwise and they will be going from right to left. Similarly, we can draw multiple field lines. Let us draw one more. Here rotation is anti-clockwise and these lines are not on the scale. Means when you draw proper magnetic field lines, their space is similar. We are just drawing by them hand. Now it is mentioned that first point, the magnitude, there is a compass, also there is a compass. So suppose we have placed here and compass. This is our compass and this is pointing needle, compass pointing needle. So what will happen? First case, magnitude of electric current in the wire is increased. So when the magnitude of current is increased, what will happen? In first case, current is increased. When current is increased, magnetic field produced is also increased. So whenever magnitude of current increases, the magnetic field produced by the wire is also increases. So it will cause, so compass will align more with magnetic field of wire. More you increases the current, more the magnetic field increases, and more the magnetic field increases, more the needle of the compass is forced to align with direction of magnetic field produced by the wire. So suppose in this case, at this point, if we find out the direction of magnetic field by the wire, as we know that magnetic field is at any point is tangent to magnetic field line. So now here magnetic field is rotating like this in anti-clockwise direction. So if we find at this point the direction of magnetic field line will be something like this. So this needle has to align to this direction. So this needle will start pointing like this. Okay. Now the compass needle is displaced away from the wire. Now when this compass is displaced away from the wire, what will happen? Suppose we move it out of the magnetic field. Now as it is out of this magnetic field, the only magnetic field acting on this compass will be Earth's magnetic field. So it will orient itself according to Earth's magnetic field. Suppose uh, now its new position will be like this. Now due to Earth's magnetic field, suppose this orientation, it orients in this direction. So what will happen that as we move this into magnetic field of wire, then it will orient according to magnetic field of wire. and as we move it out of magnetic field of wire, then it will orient itself according to magnetic field of earth. So compass orient itself according to nearby magnetic field. When it is in magnetic field of wire, it will behave according to magnetic field of wire, and when it is out of magnetic field of wire, then it is in magnetic field of earth. So it will behave like a magnetic field of earth. Okay. So with this, question number 18 is complete. Let us move to question number 19. So in question number 19, explain why electrical appliances are connected in parallel in household and why it is done. It is done so that we can prevent any damage to electrical circuit that can be caused due to overloading on electrical circuit. We have discussed this theory in detail in our theory videos, and I think it was in video number 5, domestic circuits. You can watch it on our channel, and you can find that video in our playlist. So it is done just to avoid overloading of the circuit. That's why we use parallel connections, and there are additional benefits of parallel connections and some disadvantage also of using parallel connections. That all we have discussed in our theory video. You can find it in our playlist and on our channel. We have made a detailed video on it. So with this, we have completed question number 19. Now moving to question number 20. So in 20, draw a pattern of magnetic field lines or a solenoid through which steadily current flows through it. So we have just made explained and drawn magnetic field lines for a solenoid in our previous question, where we have compared magnetic field of solenoid and bar magnet, and we have also covered this question multiple times in our previous numerical series of these videos, and also in our theory class, and so you can watch it over there, and you will be able to find your answer. So we will skip it over here. Now moving to question number 21. What is the role of fuse used in series with any electrical appliance? This question we have already discussed in our previous video. Why should a fuse with defined rating should not be replaced one with a larger rating? This question also we have discussed in our previous video. So you can find them in our previous video, in our question, I think video number 6. So please go and watch that previous video, and we have also covered this question in our first or second videos also. So you can also watch those videos and you will find your answer. So with this, let's move to question number 22. So let us now move to question number 22. In question number 2, we have to draw a semantic diagram for common domestic circuit and discuss the importance of fuse. So let me show you a common house domestic circuit diagram. So here you can see a common house domestic circuit diagram. Here we have three wires. One is earth wire, the red one is live wire, and the black one is neutral wire. So you can see that only live wire is connected with the fuse, not the neutral wire, because most of the current flows through live wire. So it is first connected through fuse, then it is connected to electric meter. This meter records amount of electricity you are using on daily basis, and then a monthly bill comes according to reading of that meter. Now this red wire or this live wire goes to electrical distribution system. This distribution mostly has fuses. Here we have individual fuses for each appliance or each room depending upon the load. Where in case of main board we have one fuse for whole house, and here we have separate fuses for each appliance if it is very high load appliance, and for each room if it is normal connection. Now for these out of these fuses we separate power in parallel connections to each our room or each appliance, and there is a third wire, green wire, connected to each appliance so that we can provide proper grounding in case of any short circuit happens. And what is short circuit, how it happens, this we have already discussed in our previous videos, so you can go and check out our previous question series videos of this chapter, and you will find that how we have explained that short circuit mechanism, why there is parallel connections, can we make series connections or not. All this we have discussed in our theory videos and numerical series videos also. So you can go and check out there, you will find the answer. Now in second part it is mentioned that why should we replace burnt fuse with identical rating fuse. So this we have already explained that if we replace any fuse with higher rating fuse, then what will happen? Suppose we have a device. Suppose this device works only up to 3 ampere. If current more than 3 ampere flows through it, it will get damaged. Now, due to some short circuit, its fuse of 3 amperes get damaged. Now, if we replace it with suppose 4 ampere, we replaced it with 4 ampere fuse. Now, this fuse can allow maximum current of 4 ampere. So, whenever current exceeds 3 ampere, this fuse will not melt, and current of 4 ampere will flow through this circuit, and whenever current of 4 ampere through this circuit, it will damage this appliance and fuse will not get melt, and so it will not do its work because we have replaced it with a higher rating fuse. It will only melt when current of 4 ampere flowing through it. So that's why we should not replace any fuse with higher rating. We should replace it with identical rating value. So that's how question number 22 is completed. Let's move to question number 23. Write 4 properties of magnetic field lines. This we have already covered in our first video of this numerical series, and also in our theory classes. Now, second part, 2 uses of magnetic compass. So, with the help of magnetic compass, what we can do, we can navigate and we can find direction of magnetic field. These are the 2 uses. First is we can use compass to navigate or to find directions. This only works when there is no magnet around you. If there is some magnet around you, then it will not work. And second, to find direction of magnetic field. So these are the 2 uses of a compass. Now let us move to our next question. What is solenoid? Draw the pattern. We have already discussed it. What is pattern of field lines inside a solenoid? What do they indicate? So pattern of field lines inside a solenoid is just like a bar magnet. They move from south to north, south pole to north pole, and they are equally spaced. It means there is constant magnetic field inside the solenoid, and also this we have explained in detail. We have already covered this type of question in detail in our previous videos. Now, next part is how is the magnetic field produced inside a solenoid? This we have already discussed. How can this field be utilized to magnetize a piece of iron, soft iron? So how we can make electromagnets? We have discussed that this part in how we can make electromagnets. What we will do that we will take a solenoid. Suppose this is a solenoid. We will connect it to a circuit, a battery, and a resistance. So what will happen? There will be magnetic field produced in the solenoid, and suppose this represents the magnetic field line. Now suppose we have a soft iron piece, this, and we want to make it permanent magnet. What we will do? We will take it and we will place it inside the solenoid, and when it is placed inside the solenoid, then there is changes happen in magnetic structure of the iron, and due to those changes, when this piece is brought back, when this piece is brought back from inside, suppose we place it inside the solenoid, and when we bring back this piece again out of solenoid, then this piece we will find that this piece started behaving like a magnet. That's how we make permanent magnets of any shape. We just uh, 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 whenever we want to make any permanent magnet, we just take iron and give it the desired shape. Suppose we want to make an force magnet like this magnet. We want to make magnet of this shape, then we just make the shape or bend iron in this shape, and we will place this shape inside a solenoid. After some time, then when we bring this shape out, then we will find that this started behaving like a magnet. So that's how you can use solenoid to make permanent magnets of soft iron, and that's how actual magnets are made. Because the magnets we find in nature, they have very weak magnetic field, and which has no any practical application. So to make magnets of practical application, we make use of solenoid and soft iron bars to make magnet of desired shapes. Now, moving to question number 25, you are given three identical looking bars, one of which is magnet, the other of magnetic material, and third made of non-magnetic material. Using just three bars, what will you find, and how you will identify that which one is magnetic and which one is non-magnetic and which one is only magnetic material. So for this, let us clear the screen. Suppose now to solve this type of question, suppose we have three bar. Number one, this is bar number one, this is bar number two, and this is bar number three. Now suppose bar number one is made of magnet, bar number two is made of magnetic material, and bar number three is non-magnetic material. So first of all, discuss their properties of all these three type of bars. So when we have something made of magnet, so what it will do? It will exert magnetic field. So if it is made of magnet, what will it cause? It will cause its magnetic field, and it can attract and repel magnet and magnetic material. Okay. Now, if bar is made of magnetic material, it gets attracted towards magnet, but but it does not have any magnetic properties. Okay. Now moving to third, non-magnetic material. They do not respond to magnets. Means they neither attract nor repel to any kind of magnet. So suppose we take bar number 1 and bar number 3 and we uh, bring them together closer. So this is bar number 1 and this is bar number 3. If we bring them closer, then we will find that there is no force acting between them. So if there is no force acting between them, then there are only two possibilities. Number one, so in this case, but we will observe that no force acting between them. So what are the possibilities? Possibilities. Possibility number one, both are non-magnetic, means both are normal material, so they will not exert any force on them. Number two, one of them is non-magnetic. Now we know that both of them are non-magnetic. One of them is non-magnetic and one of them is either magnetic material or magnet. So till now we don't know which one is which, but we are sure that one of them is non-magnetic. Suppose, so to find which one is non-magnetic and which is one is magnetic, what we will do to solve this problem, we will hang them freely with some thread, and thread should be attached in their middle. Thread should be attached in their middle point, something like this. That suppose this is our rooftop and we hang them like this. This is suppose our thread and these are our bars. This is bar number 1 and again this is thread and this is our bar number 3. Now we give them random orientations. Suppose we push this bar from this side and this bar from this side, so we can give them random orientation. Now we know if one of them is a magnet, it will align according to magnetic field of Earth. So if any one of them is magnet, then it will align in Earth's magnetic field in north south direction, because we know when we freely suspend a magnet, it's orient itself in north south direction according to Earth's magnetic field. So we will find that bar 1 is doing this, that bar 1 is orienting itself in north south direction. Whatever direction in it we will rotate, it will finally orient itself in north south direction, and bar 3 is not doing this. So using this we can identify that bar 1 is made of magnet and bar 3 is made of non-magnetic material. Now we have only left with bar number 2, and as in the definition it is given that we have three, and one of them is magnetic, one of them is magnet, one is second is magnetic material, and third is non-magnetic. So we have identified magnet and non-magnetic, so the remaining one is magnetic material. Same process can be done using 1 and 2. We can bring them together and then both will attract each other. So either both can be magnet or one of them can be magnet, then we can freely suspend them. When we freely suspend, then only magnet will orient itself in the direction of magnetic field of Earth, and no magnetic material will not also orient itself in Earth's magnetic field. So magnetic material will be in some random direction, but magnet will always be in north to south direction. That's how we can find out that which one is magnetic, which one is non-magnetic, and which one is made of magnetic material. So with this question is complete. Let us move to question number 26. And if you are finding our work useful, then you can support us by scanning this QR code. So let us move to question number 26. An electric fuse has a rating of 3 ampere. So maximum value of current is given 3 ampere. In connected in a circuit with electric iron to power. So we have power and electric iron. Its power rating is given 1.5 kilowatt. So power is 1.5 kilowatt or 1500 watts. Now it operates at 20 volts. So it is not 20 volt. It should be 200 volt, at least 200 volt. So potential is 200 volt. Now we know that power is voltage into current. So value of power is 1500 equal to voltage 200 and I. So from this we can find value of current for this iron is 7.5 ampere. Now what will happen? This iron, this electric iron will draw current of 7.5 ampere from the circuit. But our fuse only allow 3 ampere. So what will happen? Fuse will blow or melt and circuit will be broken and electric iron will not function. As circuit is broken, no current is flowing through electric iron, so electric iron will not function. So this will happen. So according to this rating, this potential, we have to raise the rating of fuse, or we have to replace it with rating of 7.5 ampere at least, or more practical to be 8 ampere. We have to replace it with the rating of 8 ampere fuse. Okay. So with this question number 26 is complete. Let's move to question number 27. Now we have only two questions remaining in this exercise. So moving to question number 27. It is similar to our previous question. Here again power is 1500 watts. Now potential is given 220 volt and current rating for fuse current rating for fuse is 5 ampere. So if we now find the using the power formula, power is voltage into current. So for iron it is 1500 and potential is 220, current is I. So what we will find, I is equal to 1500 by 220. So it will be 75 by 11. So again it will be approximately 7 ampere. So our circuit, our appliance will draw 7 ampere of current, but our fuse can only allow 5 ampere of current. So again fuse will blow, fuse will melt, and it will not allow current to go beyond 5 ampere. So fuse will blow, circuit connection will be broken, and our appliance will not work. If we want to make it work, then we have to replace this 5 ampere fuse with at least 7 ampere fuse. Okay. With this, question number 27 is complete. Let's move to last question. In last question, question number 28, we have to name three factors on which the force on current carrying conductor depends. So we know from the formula that force is VIL sine theta. So what are the three factors? Factor number A is applied magnetic field. Applied magnetic field, and how it will affect that if magnetic field increases, force will also increase. Second is current through conductor. How will it affect? If value of current increases, then value of force also increases. And third is length of conductor. And again, if value of length increases, then force will also increases. There is fourth one also, that is theta, and theta is between length and applied magnetic field. So for force to be maximum, theta should be either 90 degree in positive direction or 270 degree. If we want force to be maximum in negative direction, so theta can attain any value of 90 degree or 270 degree. In this, force will be positive maximum, in this force will be negative maximum. Means if this force act in right direction, then this force will act in left direction. So with this, our third question series, our third question exercise is also complete. Combined, we have completed more than 100 questions. And if you like our work, then please do like this video, share this video, and subscribe to our channel. Because more you share, more you subscribe, more we feel motivated to make such content, and more we get feedback that whatever we are making here is useful or not to people from whom we are making it for. And also, if you want to support us, then scan this QR code and support us with whatever amount you can. And this amount help us to get new books and uh, new hardware, computer hardware, so that we can make more of these videos comparatively easily. So with this, uh, we will meet in next video, and thanks for watching. Keep on studying.